Hello and welcome to the lecture for MRI the Basics Chapter 13, which is all about the data space. For our distraction here for today, or a picture of the day, is from this technique called Quantitative Susceptibility Mapping, which at the end of this lecture we'll discuss how we can use image phase. Actually, we're used to looking at image magnitudes, but actually the image phase can give us some interesting contrast about iron composition, even tissue orientation, and this is really a neat and relatively new technique within MRI. Okay, so the learning goals for today are actually to talk about a lot about K-space, which is our data space. So what is it? I want to know the concepts of what is spatial frequency, or what do the different locations in K-space represent? Then, how do our magnetic field gradients determine where we sample data in K-space? And finally, how do we create images from K-space? And then we're going to go into a couple more specific topics. What symmetry can there be in K-space, and how does this make so-called fractional next methods work? And then understand that MRI includes both magnitude and phase images, just like the example I just showed. So let's just repeat what we learned here about spatial encoding, which is that call I told you to the process of image construction is we have a frequency encoding gradient on always to encode one dimension, and to encode the second dimension, we're going to do these steps through different values of K-space and so on to fully encode our image data. And so we just briefly introduce this concept of K-space, and that's what we're going to elaborate on a bunch today. So what is K-space? So if we think of what we want, which is our image or the image space, which are sometimes referred to as the spatial domain, X and Y. K-space is the spatial frequency domain. And what that is it's a Fourier transform simply of our image space data. Here's one example for a brain, and another example for another a phantom object, an object used to test an MRI scanner. And the first thing I want to cover is, well, what does it mean to, we're going to bring up some terms called the K-space trajectory, and really there's a very specific relationship in terms of how the gradients that are applied after the RF pulse, such as frequency and phase encoding, these actually determine where we're filling in data in our K-space data matrix. And the relationship that we're going to derive here is that this below, that the K-space location is determined by the cumulative area of the gradients. And the term we'll begin to use here is this concept of a K-space trajectory. And this is going to refer to the pattern by which the magnetic field gradients create in the spatial frequency domain. Okay, so I just dumped a lot on you there. Let's go through each of these things more specifically. So to motivate K-space, I'd like to draw a simple pulse sequence here. You have some RF excitation. Then we're going to turn on and off a magnetic field gradient. And we want to look at the behavior of net magnetization. At 4 different points in time here. And then specifically look at the phase that's accumulated of the net magnetization. So after our RF pulse, we're going to tip our net magnetization here into the transverse plane, this being time 1 here. And then, as you recall from our discussion of frequency and phase encoding, during the magnetic field gradient, there's going to be a frequency offset, so there's going to be some net phase that accumulates of the net magnetization, so it'll experience some rotation. And in this picture, the gradient continues to be on. It will continue to experience rotation. So remember, during this time, we've created frequency as a function of position. But one important thing to note is as soon as we turn our magnetic field gradients off, then there is no change in the phase. We've removed this variation of frequency as a function of position. Okay, so one way that we can characterize this is in terms of this phase angle that we're accumulating. And this is a way that we also looked at phase encoding. And we can describe the gradient as creating some phase during the period that the gradient is on. And then when we turn off the gradient, just as in phase encoding, right, there's no additional phase that's accumulated here. And we can add some values. So during this time interval here, we know that the frequency is gamma bar times, say this is our GXR, times position in X. And so what that means is if we say, oh, this is time 0, then during this interval here, say to time t, the phase that accumulates in this interval is going to be gamma GXR X times t. Or I'm going to define this to be this, generally this phi x times the x position here. I'm saying that we could make this, we know that it's going to vary as a function, linearly as a function of x. So, and this only applies, remember, during this interval. And therefore, this value out here is going to be what our the total amount of phase that has accumulated during that gradient. So just evaluating this equation at time t equal to capital T. This is going to be basically the phase effect of our gradient as a function of x position. Okay, now let's go to a little bit different example. Say, what if I do something like, now what you've actually seen a little bit in pulse sequences, where we're going to turn our gradient on, off, and then turn it in the reverse direction as well. And we can start off by looking at this from the net magnetization perspective. Get some tip down of the net magnetization. Now, just like the result from before, we'll have some rotation by some angle during that first time period. During the next time period, the magnetization is, there's no magnetic field gradient, so the magnetization is frozen at that interval. And then during this final time period, since we've reversed the polarity of the magnetic field gradient, that actually creates a rotation in the opposite direction. And we're going to set this up so that this is net zero accumulation. How do we do that? Turns out we do that by making these gradient areas equal. Or if this was GXR, we make this to be minus GXR, and we can use the same durations here, so that the initial phase accumulated here is going to be that final phase that we had in the last slide, and then the size of this angle that it moves back is going to be minus. Since a minus GXR, it's a minus accumulation. So if we set these two areas to be equal, we're going to have a phase accumulation. Looks like this, nothing with no gradients on. Going to accumulate phase to some positive value here after the first gradient. No phase accumulation when the gradients are off. And then the reverse gradient actually creates a reverse accumulation of phase, and in fact we can cancel out the effects of our magnetic field gradients. So what I'm building up here is that we need a way to characterize this generally of turning on and off, reversing different amplitudes of our magnetic field gradients to capture the range of things that we can do and that are going to be useful for MRI. So actually this phi x here, this is the picture drawn before in the phase encoding examples in particular. This term, we can actually replace this, and this is actually proportional to our k-space value in x. And what you'll note from this picture is that actually the phase angle that we get depends on the cumulative effect of the magnetic field gradients. So as we do more gradient, we get more angle in one way. If we stop, turn off the gradient, we get no accumulation of effect. We turn it on the opposite direction, we get accumulation in the other direction. And in fact, the k-space in x here would be defined as gamma bar times the integral from 0 to whatever time we want to look at of the x gradient. Oops, d tau there. So I mean we can do the calculus, but we'll usually look at it in examples where we can just look at use the intuition from this that tells us that it's the gradient areas that are important. So what you want to remember with the k-space definition is this is cumulative area of the gradients. And so in this example, since the cumulative area is this positive amount plus this negative amount, they cancel each other out. And we would note that our net phase accumulation or k-space location is going to be 0. This handles the case of 1 dimension. Let's go on to a case of 2 dimensions. And what I want to show you here is that these the gradients can be the effects of the gradients are independent of each other. So there's a phase or the k-space in x and the phase of the k-space in y, and these are going to happen independently. look at our 4 times. Is 4 a magic number? I don't know, maybe. And in this case, let's start off by considering a couple of different locations. So let's start off by considering a location out here. So this is our object space or our image space. To clarify, that's not from the net magnetization. So, and then let's think of what do we have a couple of relationships that we should add in here to help guide us during this interval here. Or the frequency is the have frequency accumulation, and I'm going to mimic the we have frequency accumulation as a function of x during this interval. If we now have a y gradient of some gradient in amplitude, our result from phase encoding was that the phase here is going to be equal to the gradient area times the y position. Okay, so let's have these effects here. So that tells us first that our red object is tipped down, and this first gradient has no effect on this object because its y position is 0. But then during the frequency encoding gradient, as the earlier example, it's going to accumulate some net phase, and then during that, again, it's not affected by this reversed phase encoding gradient. And let's consider the opposite case of that, where we have some y offset, but not an x offset, bar net magnetization in the transverse plane. Now, the first gradient does create some net rotation of this object. Okay, but when it comes to the gx gradient, this has no effect. And then, as in the previous example, this final y gradient is going to rotate back to the its original position. So we're basically unwinding the phase in y. So these two cases of alone, we can use those to map the phase in x. No accumulation of phase that is a function of x position. And I have some net phase accumulation during this gradient, and it's going to be turned off. Then in y, phase variation in the y direction is going to accumulate to some value. It's not going to change by the x gradient because there's no effect in y position. And so what the overall relationship for the phase here is that of any spin is that this phi x times the position in x is phi y times the position in y. And this is what we're seeing in the plot below. For when the y is 0, we're only getting the effect of the phi x drawing here. When the x is 0, only getting the effect of phi y. And of course, we can have an object that has both x and a y offset. It's going to get a little messy, but let's check it out. So it is rotated by it gets some term from the y phase or the y phase gradient, the first interval. Then it's going to be rotated further during the frequency encoding gradient. And then at the end here, it's actually going to rotate right back to this location where the y effects are totally gone. This phi y, or the effective y gradients, are canceled out. And we only have phase that depends on the x position. And so in fact, what these two lines here represent, this line actually represents kx, and this line here represents ky. The only difference is basically a 2 pi term, where if now I add the definition of ky, which is gamma bar times integral, now simply just of the y gradient. We put this together over here, and actually the total phase of our net magnetization is simply going to be 2 pi times kx times x plus ky times y. Okay, so again, stepping back, what we're doing here, as we're saying, we can characterize our gradients by looking at the phase they create in our net magnetization. And the phase that they create is, we can characterize it by k space, by these k terms, which are the cumulative area of the magnetic field gradients over time. So we'll often look at this in terms of the k-space trajectory, and let's say, now let's use the k-space notation instead of the phase notation. I have an RF pulse, and let me just repeat with the same example that I showed there. And so if we simply, what this picture tells us is, first, our phase at the beginning is always 0, or our k-space, and we can denote it as a vector, is 0 after the RF. So after excitation, k-space is always 0. So back to my colors, so we can, if we look at this time here, that corresponds to when we're going to be looking at what we call our k-space trajectory, or where, and this reflects where we are sampling data, where we're getting information, what information we're getting about our object. That we plot it like so. So we look at, okay, you have this initial interval, we have some phase accumulation in y, the phase encoding gradient, no accumulation in x. So we would draw this as a k-space trajectory. Kx is fixed, but we're moving, or we're traversing to some location in ky. And where we are here can represents the when we acquire data, what information we're getting about our object, what spatial frequency information we're getting about our object. Okay. In our next interval here, we said we have phase accumulation or k-space traversal in the x direction, but the y direction is fixed. So that would be represented by we start here, we move our trajectory along the y direction. Then the final interval here, nothing is changing for x, but we've reversed the phase accumulation from the y gradient, or the phase accumulation y, in terms of the k-space trajectory, that looks like this. What this means when we're on like this axis, we're no longer encoding any information about the y direction. We only have some phase encoded in the x direction. And so this is really to illustrate the concept of the k-space trajectory. We'll discuss a bit more next here. So, and here's the full k-space equation, where we can look at k-space as a vector of kx, ky, even kz. The magnetic field gradients as a vector gx, gy, gz. And this is the equation that I wrote on the other pages, just expanded into the vector form. And now let's modify the examples slightly to look at how we go across k-space by first starting with a negative gx gradient. And in terms of the k-space perspective, what that does is it means our k-space trajectory goes from the center to the left in k-space. Then what would happen here when we turn on our frequency encoding gradient, and where you know where we acquire data normally, is that now you're going to traverse from left to right, or negative to positive, just in the kx dimension. So this is our conventional frequency encoding, where we're gathering information, but we know in this experiment where we have no information about the y direction here, because we haven't used the y gradient, or in the k-space perspective, we haven't gone anywhere in ky. And then as sort of an example here, we can also unwind or return to the center of k-space, where we basically removed any of the phase accumulation due to the magnetic field gradients. So this is the k-space perspective for our frequency encoding experiment. Now what happens if we add phase encoding? Now it's going to look like the example that I drew a couple of slides ago, where if you combine both this negative gx and then a gy, we're going to go at this angle. So slightly different than the example I showed, but this is actually more realistic to how we acquire data. So now we have some encoding, or we have some position in ky that we've traveled to. And as we know, what we do for our 2D-FT experiment is we next are going to just apply the frequency encoding gradient. And this is now where that picture you've seen a couple times comes from, of that the different phase encoding amplitudes ends up filling these different lines, or different data in our k-space encoding matrix, our data matrix. And as an example here, we can also unwind, we can reverse all the effects of the gradients, which is equivalent to going back to the center of k-space. And so we know that our phase encoding experiment is actually going to be doing a number of these different phase encoding amplitudes. And if we look at that from the k-space perspective, it might look like this for a different phase encoding step, where now we've sampled a different line in our k-space domain, our spatial frequency domain, so in k-space. So now putting these side by side by the picture you've seen before, this is where that picture you've seen before comes from, is that as we increment our phase encoding gradient in the k-space perspective, what we're doing is we're going between these different lines in the ky dimension. And then when we're doing our frequency encoding gradient, we're reading out the data in the the kx dimension of our data matrix, or our data space. And we normally, by convention, have x be the frequency encoding gradient, but that doesn't mean we can't, in fact, do encoding in a different way. We could say play a Y gradient like this, in which case, if we acquire data during this, we're going to get that the data on these lines in the spatial frequency domain or in K-space. So what do we want to do here with this this new formalism, K-space? How does this impact how we create an image? And basically, you can describe the goal of sampling K-space or having our gradients change so we move across the K-space trajectory in the spatial frequency domain is we want to sample some 2D region, and this is typically a rectangular region with the type of imaging we described, 2D-FT imaging. We're going to do a line, a line, a line, a line, and overall this will accumulate a rectangular region, just like you see in this example here, right? I can display this as a rectangular image because it was acquired with this 2D-FT imaging, though we can also make this sort of ellipsoidal shapes as well. And then it turns out to reconstruct our image, we need to, as long as we know where we are getting data in K-space, we can do an inverse Fourier transform and convert this data into our image once we've sampled this large enough region in K-space. So here's our, going back to the example before, again, this would be our full kind of K-space trajectory of a 2D-FT imaging, and now I've just drawn lines in purple here where actually are acquiring data, so not including what are something called the pre-winders, the rewinders that were going out and back to the edges of these lines. So just focusing on the parts where we know that we acquire data during the frequency encoding gradient. And we're going to stack up these lines of data. And we know that these lines of data, in fact, represent the spatial frequencies that are present in our image. And we'll unpack that statement a little bit more next. Yeah, so putting this together for the full pulse sequence here of the 2D trajectory. Now, this is not the only way that we can acquire data in MRI. There are other trajectories that we can use. We can do, and we'll talk about, in particular, we'll talk about echoplanar imaging or EPI, which is a way we can, and understanding all of these techniques is really founded on using the K-space formalism or the K-space perspective to characterize the effect of the magnetic field gradients on the data that we acquire. And so we have these echoplanar imaging, which is doing like stacking up multiple lines of K-space in a single shot. We could do this radio imaging that I described briefly as sort of one of the original methods applied for MRI. There's other fancy stuff, one called propeller, where they use these blades of K-space data and move them around, or spirals, which are very fast. We're mostly going to focus on 2D-FT and then echoplanar imaging, which is sort of an extension of that. Okay, so we figured out, okay, gradients, we can characterize their effect on the phase, and we refer to that as K-space, and then I've said, well, the data you acquire there is, in fact, the spatial frequency domain information about our object. So let's dig into that and say, well, what does K-space represent? So the Fourier transform is going to become very important in this understanding. And what these pictures at the left are representing are what information is provided by a single point of data in K-space. So at our central point in K-space, Kx and Ky is 0. That's where we have no phase we've created across X or Y. The data at that point corresponds to anything, the part of our image that has zero spatial frequency, that's completely constant across our image. Whereas if we move away from that central point in K-space, now this data is encoding these different spatial frequency patterns. For example, on the top left, that's one of the furthest parts away from the center of K-space, so it's in the high spatial frequency area, so it has the fastest oscillations. It's representing the fastest oscillations in our image, the points. And then since it's at this kind of angle, and it both has some ky and some kx, that means it's encoding information, high spatial frequencies at this specific angle. Whereas the bottom two examples are either on the ky or the kx axis, meaning they're only representing information or components of our image that are changing in x, or components of our image that are changing in y. And then some other intermediate point here. So another way we can think of the Fourier transform when we're looking at the concept of spatial frequencies is that what the Fourier theory says is we can decompose this image, this nice brain here, into any image into a set of spatial frequency patterns, just a subset of which I pulled out here. And the only difference between this image and, say, the image of somebody else's brain is going to be the weighting of these different spatial frequency patterns. So this is what we need to know. This is going to be our case-based data. And so the way we can reconstruct, or the way we can represent this image, is we can say, okay, we've got this big set of various spatial frequency patterns. We're going to pick how much of each of these spatial frequency patterns we're going to use to create this given image. So that's what these little circles with the crosses in them represent, is multiplication by basically the weights of our different spatial frequency components. And then we add all them together to create the image. And what's going to be different between, one person or another, or a different type of contrast, is that these, not the spatial frequency patterns, those are fixed by Fourier theory, but are going to be the weights that are applied, and those are going to change how our image looks. So really the entire process of the MRI reconstruction can be illustrated in this way, whereby what we're doing, the data we're getting, is data in K-space. And we're going to take these data points we collect, and we determine which data points we've collected by taking our gradients and deriving the K-space. We take these data points we've collected in K-space. Each one of these represents a different spatial frequency pattern in the image. So we multiply whatever we've measured at that data point by the spatial frequency pattern. We sum them together, and we should get the image of our net magnetization. And really, this is all just describing the Fourier transform, but from image domain perspective, a 2D image domain perspective. Okay, so I want to show these examples here, these movies. So this was the illustration I showed before of this fact of then, remember that our gradients are creating this rotation of the transverse magnetization. And basically the pattern of the phases that we have over here corresponds to our location in K-space. So it's a little hard to see when we look at the individual net magnetizations. But if I, first here, here's a more realistic case where we use this initial dephasing gradient. And then we can see here the K-space trajectory itself is also being plotted. And you can see that different points in the K-space trajectory correspond to these different patterns of the phase in the transverse magnetization. I'll let that go through one more time here and repeat that again. Our gradients are creating these phase patterns of our net magnetization in different dimensions. And it's basically these phase patterns across our spatial dimensions that define what our K-space location or K-space trajectory is. And so this is a little bit easier to see if, in fact, we, rather than looking at the individual net magnetizations themselves, if we simply create an image of the phases of the transverse magnetization. And these phases here correspond to those spatial frequencies that were shown on a few slides ago. So you can see as we're in different points of K-space here, again, you get a pattern in the phase that corresponds to those spatial frequency patterns that I showed a couple of images ago. And this is exactly how we're encoding those different spatial frequencies, is we're encoding them in the phase. It turns out by encoding them in the phase, that's how a Fourier transform works if we look at that equation. And if you'd like to look at these again, they are in the Spatial Encoding notebook in the GitHub MRI education resources. And this is a fun example here to say, look, we don't show the case for a spiral K-space trajectory. And again, we're also creating this rotation or these phase patterns in our transverse magnetization that depend on the cumulative effect of our magnetic field gradients. And at the beginning, the change in, if there's not very much phase across the object here, but as we go further and further out in K-space, or we have more and more gradient area accumulated, we have more and more sort of dispersal, so the difference in the phase of these transverse magnetizations. Okay, so I want to talk here about a few properties of K-space that, again, I think will help to illustrate what this data is and what information we're getting during our data acquisition as we traverse K-space due to our gradients. So the first property that is generally see is that it's at the center of K-space, which represents the low spatial frequency information. So the components of our image ultimately that vary slowly across the image. These typically have the highest amplitude, and really for MRI data, and in fact for most natural images, the center of K-space or the center of the Fourier domain contains the majority of the energy. But that's not enough to get a high quality image. We need to also acquire our edges of K-space, which typically have quite a bit lower amplitudes. But they encode this very important high spatial frequency information that we're going to need to, for example, create edges. So here's some examples of that. So this is an example of an axial brain image, where the top example shows if we took only the low frequency K-space data and we try to do a Fourier transform to reconstruct the image, and what we'll see is a relatively bright image. That's because of this high energy or high amplitude in the center, but it's also very blurry. And this is because we're only capturing low spatial frequencies, so features that are varying slowly in the image. Versus if we exclude the center, so the low spatial frequency, and only include the high spatial frequency, then we see this fantastic image of the edges, which are represented by these high spatial frequencies, but we also see it's much noisier, and we don't see these more slowly varying contrast features that are also extremely important. And here's another example of that in this sagittal brain image, also showing the case of, well, if we actually use both the low frequency and the high frequency data together, of course we get an image that's going to be more like what you will be used to or start to see more and more. It includes both the low frequency slowly varying information and the high frequency variation. And because the Fourier transform is linear, since the full data equals the low frequency plus the high frequency. The full image equals the low frequency image plus the high frequency image. So this is, watch quick here, this is an illustration of as we acquired data line by line in 2D-FT image. We just took the data as it comes and we can reconstruct the image. This is what it would appear like, and once we hit the center of K-space right there, then we see a huge amount of information is filled in. We get this low frequency information, and by the time we get to the end here, we've actually captured a lot of the information for our image. The next example will start at the center of K-space. So if we start accumulating data at the center of K-space, first thing we do is fill in the low frequency information. And then what we're going to see as we progress more and more here is, and it becomes more and more subtle, but we're starting to better define the edges, particularly in the up-down direction of these images as we go further and further out in K-space. The next example is sort of a random ordering. So if we randomly grab our phase encoding lines in K-space, sort of randomly be filling in information, and you notice that all this artifact, now we would call this a ghosting or an aliasing artifact, appears in the direction of our phase encoding because this is the incomplete dimension of our image here. But eventually we get to the same result. And finally, here's a case, so if I just really grab random 2D points and slowly fill in the image here, eventually we'll get to the nice image, but you still see these kind of weird artifacts until quite close to the end here. So some fun examples, I think. Okay, so here we're going to switch gears a little bit and talk about a property of our K-space data and our images that can really help the way we acquire data and in fact accelerate our imaging. So this property, the property of conjugate symmetry in the Fourier transform, is that a real valued function has conjugate or Hermitian symmetry in the Fourier transform. So if we have some function f of x that's real valued, then the Fourier transform of f of x, so capital F of kx, that at every location at kx, if we look at negative kx, so we go to the negative location, we have the negative location, the value of the function or the Fourier transform is the same, except it is the conjugate. So that means that the imaginary part of is inverted. Okay? Or more generally, we can convert this to multidimensional. So we have some f of multiple dimensions that's real valued, then capital F of our multiple dimensions k, and has the same conjugate symmetry property. Okay, so what does that mean for us in MRI? Say we have our subject here, the brain back here, and what we typically mean by real valued, when we think of that, is that all the transverse magnetizations after RF excitation are pointing in the same direction. This is equivalent to why pointing in the same direction after RF. Or we would say, and I'll introduce a notation often used, that our object, I'll use the notation lowercase m, in space is real valued. So then we kind of take the Fourier transform, and we look at the K-space of our object, which is what our data is going to be. We're going to be acquiring the K-space, the spatial frequency data for our object. That what this property of conjugate symmetry says is, well, if I measure this point here, so some location, kx, k, y naught, and then I look at the value, so I have m at this location. If I look at the value of m at minus that, I can actually figure that out by simply taking the complex conjugate of this other data point. So what this really means is that we can acquire one data point, and then we can copy the value to the other side of K-space without actually having to measure this other value in K-space. So this is the idea behind the techniques that are called like fractional nux or partial Fourier. And first I want to describe the ideal case, which is called half nux. And what we're going to do in this case is we're actually just going to acquire our K-space data on 1/2 of K-space, so we can, and this can either be half of the frequency encode or half of the phase encodes. And then we're going to synthesize the rest of K-space by like so. So we're going to take, we're still going to have the data that we acquired. But then what we're going to do is, for example, we'll take, let's think, and we'll take this data down here. It's going to point in the opposite direction. So like these locations map here. So we're going to map it to the negative points. And we're also going to perform the conjugation. And we're going to do this for all the data that we've acquired. Okay. And we're going to be able to fill back in all of our K-space data by only acquiring half of our K-space data. And so potentially here, I'm going 2 times faster with this type of technique. So we're doing this based on now understanding that, first of all, that our data we're acquiring is in the K-space or spatial frequency domain, and then looking at some of the Fourier properties of the spatial frequency domain that we can take advantage of. So this is the ideal case. Practically, it turns out that our objects are not exactly real valued, they're partially real valued, or they have some low frequency phase on them. And if you're interested, there's some you can get some more information on this topic. I'm just going to give you the overview of what happens. And in this case, what happens is you actually just have to acquire a couple extra lines in K-space. So the oversampling is this little bit here. And then this is where it would be fractional next, like say, if we normalized and said, well, the whole amount of data we need is 1. If this is 0.6, this would be sometimes referred to on the scanners. We need to set this up as, say, next 0.6. And so this is what we would acquire. And then there's a slightly more sophisticated reconstruction procedure, a couple of different ways to do that, but you can basically take all, and so I'll just illustrate it by the fact we're just going to end up being able to fill in our entire case-based data, and you have to do a couple of additional operations here. So it's not exactly simply just a conjugate. There's an additional pre-processing step of removing unwanted phase. Okay, but here we're still, in this, as I've drawn it, it's 40% faster. This is pretty typical, but this can range, around this value, maybe 30% faster. These are kind of typical values. Okay, so that covers it for the fractional next or partial Fourier techniques. And that also brings us to the point to remember that, in fact, every MR image you're going to see, there is an underlying magnitude and phase data from that, or it's a complex valued data. And we're not always doing this partial Fourier technique because of some of these reasons below that we'll get into. But usually are looking at magnitude images, sometimes referred to as the modulus. That's the usual diagnostic MRI it's used, but there's a few notable cases where actually the phase information is very important. And these are flow imaging, where actually encode flow in the phase. 4D flow, I think I showed an example of earlier. Susceptibility weighted imaging is good for visualizing veins and iron deposition. Also a technique called phase sensitive inversion recovery, or PSIR. So let me show a few examples of that. So this is a really nice example of a flow image where we see the magnitude image here, an axial slice through the top of the chest. And you can see the annotation here. AO is the ascending aorta, DA descending aorta, which obviously have a lot of flow as the blood is getting pumped out of the heart. And so what you can do with a technique called flow encoding is you can actually create image phase due to flow. And then what the contrast here represents, the black represents flow in the inferior direction, or superior direction, excuse me. And I'll annotate that here. And whereas the opposite phase represents flow going in the inferior direction. And then you can see this also across the cardiac cycle images below, where there's the quiescent phase here where there's really no flow, and then the flow levels increasing as we go through the cardiac cycle. There's also generally phase accumulation due to off resonance, and really coming from two major effects here. One is the imperfections in the main magnetic field. The other is magnetic susceptibility differences. And so what happens when you have these differences, particularly if you do gradient echo, at long echo times is that the spins begin to accumulate some phase. This is like the things that we discussed in spin echoes that spin echoes get rid of. But there's some cases where we actually really want to preserve this phase accumulation due to off resonance. And you can see in the bottom image here, there's both like these large, this large pattern of phase accumulation, probably the delta B terms, but there's also, you can start to see some, again, pointed out some highlights, some structure in here. It's a little bit hard to see looking at the raw phase images here. But what we can do is a technique called susceptibility weighted imaging. So using the different phase images and a bit of processing that's briefly illustrated here, you can go from these to the susceptibility weighted images. That this one here, it's a little hard to see, but it's really going to highlight veins. And then also to a technique called quantitative susceptibility mapping. And here we see things like iron deposition, because iron has a very different magnetic susceptibility than tissue. So both of these are newer techniques in MRI, but they proven themselves to be very powerful. And the last technique that relies on the image phase that I'm going to talk about is phase-sensitive inversion recovery. So we've talked a little bit about inversion recovery, and we talked about also this effect of, well, when we after you invert the magnetization, it recovers. You can excite it either when it's negative or when it's returned to positive. And we talked about this in the context, well, if we had a voxel that had a component that was negative and a component that was positive, they could end up canceling each other out. This technique uses this phase difference between the different T1s of tissues in order to improve the contrast, as you can see in the example on the top in the heart, where it's used to null, and a little more robust for nulling signals. So it's used to null the signal from the normal appearing heart muscle, I believe is what's going on there. And then on the bottom, on the bottom right, you can get some really exquisite gray-white matter contrast with the phase-sensitive inversion recovery technique. Okay, so that brings us to the end of this chapter 13. So again, the goals you want to have for this material is understanding what K-space is, what is spatial frequency, what do the different locations in K-space represent, and we can interpret that with spatial frequencies. And then what does K-space have anything to do with MRI? Well, it's this mapping, it's this representation of the effect of the magnetic field gradients on the phase of the transverse magnetization. So it's a way to characterize the effect of the magnetic field gradients on our signal and our data. And then think of how do we create images from K-space data. And then finally, we covered two other additional topics. One were the fractional next techniques. And then the other is stepping back a little bit and remembering that we're often going to see magnitude images in MRI, but there's also value to phase images as well. Okay, thanks very much for watching.